Yeah, so thanks a lot for giving me the possibility to speak here on this nice occasion. And so the main question, the main motivating question for my talk is what condition on the base field guarantees that all torsors are trivial? And so you can ask this question in various setups, and I'm mostly interested in the case of algebraic difference equations, but I'd like to talk about other cases before. So the main result is for the case of difference equations, but before going there, I'd like to talk about the algebraic case. In the algebraic case, everything is completely clear and obvious. And then the case of ordinary differential equations, that's the main motivating case. And Adam Pillay recently proved the theorem for that case. And if you want to, you can see my main result as a difference analog of Pillay's theorem. And I'd also like to say a little bit about the partial differential case. Okay. So, and yeah, in the second part, I'll talk about the difference case. So let's start with the algebraic case. So I start with a field K, and I look at the linear algebraic group over K that is acting on some variety X. So X is also defined over K. And such a variety is called a G-torsor if for any 2 points in a variety there exists a unique element in the group transforming one point to the other point. So for example, if you look at the group of the nth roots of unity, and so that's our group, that's a group under multiplication. And if you look, so if you fix a non-zero element in the base field and you look at all the nth roots of this element, then this is naturally a torsor under multiplication with the group. So what it means here to be a torsor is really just saying that any two nth roots of A only differ up to multiplication with a root of unity. Okay. So another example of a torsor would be just if you take the group itself. So the group itself is a torsor under left multiplication. And so this is called a trivial torsor. More generally, any torsor isomorphic to the group itself is called a trivial torsor. And it's not hard to see that a torsor is trivial if and only if it has a point in the base field. Okay. So, and it's an interesting question to understand. So given the group, you can ask, okay, what are the torsors for that group? And so there is this cohomology set H1, which is helpful for answering this question. So there's various ways to define H1. So you can define it using a Galois cohomology. And so I'm not going to define H1 here, but the main point of H1 is, so in general, H1 here is just a set. More precisely, it's a pointed set. So if G is an abelian group, then it naturally has the structure of an abelian group too. And the main point about H1 is that it classifies torsor in the sense that H1 is, well, it's in bijection with the isomorphism classes of the torsors. And so I'd also like to say a little bit why we're interested in torsors in first place. And so they come up naturally in differential Galois theory. So if you look at the differential field with field of constants little k, and I look at the linear differential equation over k, and if R is the Picard-Messier ring, so Picard-Messier ring is the solution ring for this equation, and if G is the Galois group, so if G is the automorphism group of the Picard-Messier ring, then it is known that if you think of the Picard-Messier ring geometrically, that is, if you look at the spec of the Picard-Messier ring, then it is a torsor for the Galois group. So that's the torsor theorem. It's a theorem of Cauchy. And another way how torsors are interesting here in the Galois theory is that H1 of the Galois group, it classifies the Picard-Messier rings for the given differential equation. So if the field of constants is not algebraically closed, then the Picard-Messier ring is not unique. And in fact, the Picard-Messier ring is unique if and only if H1 is trivial. Okay, so it's nice to know that the Picard-Messier ring is unique. So it's nice to know that H1 is trivial. Yeah, so in general, it's always good to know that all torsors are trivial. And so the question is, what condition on the base field guarantees that all torsors are trivial. Yeah. So one way to achieve that all torsors are trivial is just to put some condition on the base field. And so let's look at the algebraic case. In the algebraic case, the statement is not very interesting, but well, everything is obvious here. So a torsor, so all torsors for all linear algebraic groups are trivial if and only if the base field is algebraically closed. So one direction here is obvious. So if the field is algebraically closed, every variety has a point. So in particular, every torsor has a point. So the other direction is also not too hard to see. So the idea here is that you can think of any finite Galois extension as defining a torsor for that Galois group. And so if the torsor is trivial, the Galois extension has to be trivial, and so the field has to be algebraically closed. Now, if you look at this and you think, okay, what's the differential analog of the statement? So you now, instead of looking at linear algebraic groups, I'm looking at linear differential algebraic groups, so subgroups of the general linear group defined by differential equations in the matrix entries. And I'd like to know, so what condition on the base field guarantees that all torsors for all of these groups are trivial. And so, by the way, in the slide on the Picard-Vessier theory, I was just talking about the usual Picard-Vessier theory, but so where the groups are algebraic groups, but there are all these parameterized versions of Picard-Vessier theory where the Galois groups are actually differential algebraic groups or difference algebraic groups. And in this for the parameterized version, you also have the same properties. So for the parameterized versions, it's interesting to understand the isomorphism classes of torsors for differential algebraic groups and torsors for difference algebraic groups. Okay. And so, yeah, in the case of differential equations, ordinary differential equations, you might think that, okay, the differential analog would be just to say, well, K is differentially algebraically closed. But this is not at all the case. So in fact, Anand Pillay recently showed that some much weaker conditions than being differentially algebraically closed are already sufficient to prove that all torsors are trivial. Okay, so here's the statement. We fix a differential field of characteristic 0. So all the fields in my talk are of characteristic 0. And so the statement is that every torsor for all linear differential algebraic groups is trivial if and only if the field is algebraically closed and Picard-Vessier closed. And here Picard-Vessier closed means that the field has no proper Picard-Vessier extensions, which is the same thing as saying that every linear differential equation over K has a fundamental solution matrix in K. Okay. So what the statement really means is that so to solve all equations defining torsors, it is sufficient to be able to solve algebraic equations and linear differential equations. Okay, so even so, in principle, a torsor might be defined by nonlinear differential equations. You don't really need to solve any nonlinear differential equations to know that a torsor has a point. And again, like in the algebraic case, you can classify the torsors by a certain H1. So here, this H1 here with the delta, this is this was introduced by Colkin, and Colkin called this the constrained cohomology. And so this again, we have the property that H1 is trivial if and only if all torsors are trivial. Okay, so that's the ordinary differential case, and this is the kind of the easiest case to explain. And so I'd like to try to give you some idea of how to prove Pillay's theorem, because all the other cases are kind of more complicated, and it's more complicated to give an idea of the proof. But the basic overall structure of all the proofs is essentially the same. Okay. So I'd like to give a sketch here. So one direction is easy. So if all torsors are trivial, then the field has to be algebraically closed, just because you can think of an algebraic group as being a differential algebraic group, and you can think of an usual algebraic torsor for that algebraic group as being a torsor in the differential category. Okay, so this is why the field has to be algebraically closed. And to see that it has to be Picard-Messier closed, you can just look at this very particular differential algebraic group. You look at all the invertible matrices whose entries are constant. So this is a linear differential algebraic group. It's a group, the subgroup of GLN defined by differential equations. And then you look at, so for given matrix A, you look at all the solutions of the linear differential equations, and this is actually a torsor for that group. Okay. Yes, so people in differential Galois theory, they definitely know this. So to say that X is a G torsor here, it really just means that any two fundamental solution matrices only differ up to multiplication with a constant matrix. Okay, and so, well, if that torsor, you have a question? Oh, yeah, it's equal to, I'm so much in the difference case. Yeah, sorry. Yeah, so it should be 0 here. So the G should be a 0 here. Yeah. So if the torsor is trivial, then this exactly means that this equation has a solution. Okay, so the proof shows that if the field is algebraically closed, then all you need to know is that this, just for this very particular group, all torsors are trivial. This already implies that all torsors are trivial for all groups. So let's look at the ideas for the reverse direction. This one is the more interesting one. And so there's two steps. And the first step is that, so there's a long exact sequence in cohomology, and from that long exact sequence, it follows that whenever you have a short exact sequence of linear differential algebraic groups, such that all torsors for n are trivial and all torsors for h are trivial, then also all torsors for g are trivial. Okay, so and this kind of works like an induction principle. So you can use this statement to decompose the group into simpler parts, and so it suffices to prove the statement for the simpler parts. So for example, you can take n to be the connected component, and then so you know G mod the connecting component is finite, so you know the theorem holds for finite groups, and then you can assume, okay, that G is connected. Then you do something for the connected part, and so on. So you can decompose G, and so you can use all that structure theory for differential algebraic groups, and essentially, so linear differential algebraic groups, they compose into two types. So either they are just usual linear algebraic groups, or they are constant points of linear algebraic groups. And so for the linear algebraic groups, it's enough to know that K is algebraically closed. And now for the constant points of linear algebraic groups, you can use the Picard-Messier closed assumption. Okay. So this is it's kind of an oversimplification of the proof, but that's the very basic idea. And a similar approach works for other cases. So I'd like to say a few things about the partial differential case. So Anand Pillai and Zoe Chatsidakis, who's also here. So they have some positive and negative results for the partial differential case. But so the immediate direct generalization to the partial differential case is not true. And also, Andrei Minchenko and Alexey Ovchinnikov have a recent paper for the partial differential case. So here we have a partial differential field. So we have m derivations, and their statement is that every torsor for every linear differential algebraic group over K is trivial if and only if K is algebraically closed, Picard-Messier closed, and linearly closed. So you have, as before, in the ordinary case, you have algebraically closed and Picard-Messier closed, and now they need to add a third condition, which they call linearly closed, And what does it mean? So linearly closed means that every consistent system of univariate, linear, not necessarily homogeneous differential equations has a solution in K. And so what this third condition does, so the linearly closed condition, is essentially taking care of the differential algebraic subgroups of the additive group. Okay, so now I'd like to come to the difference case. And there's been some results in the difference case already, so also by Zoe and Anand. And they showed that so the immediate direct difference analog of Belay statements is not true. So so more precisely, so there exists an algebraically closed and PV closed difference field and a linear difference algebraic group with a non-trivial G torsion. And indeed, they give a very specific example of G, which is a particular subgroup of the multiplicative group, but it looks like essentially all of the difference algebraic subgroups of the multiplicative group would give a counterexample. So so now it's a natural question. It's still a natural question to wonder if there is not some positive result here too. And so what would be the difference analog of Anand's theorem? And so we know that we need to do something about difference algebraic subgroups of the multiplicative group. And so if you add algebraically closed become SEO closed, if you add that all torsors for all difference algebraic subgroups of the multiplicative group are trivial, then you can ask, okay, is that enough to know that all torsors are trivial? Okay. And so the answer is yes, and that's my main result. But there's some technicalities to it, and I like to go over everything in detail. So I'm not sure that everyone here is really familiar with the basics of difference algebra, so I'd like to go through that. So as a differential rings, so a ring with the derivation are the basic objects in differential algebra. So here in difference algebra, the main objects are difference rings. So we look at the commutative rings together with an endomorphism. And so for example, a typical example of a difference ring is the ring of all sequences with component-wise addition and multiplication, and with sigma being the shift operator that shifts the sequence one step to the left. And so a difference field isn't just a difference ring whose underlying ring is a field. So a typical example is the field of all rational functions with the shift that sends x to x plus 1. So whenever you have a difference field, you can look at difference equations over the difference field. So the difference polynomial ring in the difference variables y1 to yn is a polynomial ring in the infinitely many variables y1 up to yn, sigma y1, sigma yn, sigma squared y1, and so on. So whenever you have such a difference polynomial and you have a difference ring extending K, you can evaluate such a difference polynomial simply by replacing the symbol sigma with the specific endomorphism sigma of the given ring. So this is how you can make sense of what it means to be a solution of a difference polynomial. And then essentially, difference variety is the set of solutions of a set of difference polynomials. And so I'm not going to be too specific about where we look for solutions, but you have to look for solutions in a sufficiently large difference ring. And sufficiently large essentially just means that you are able to recover the equations from the solutions. Okay, so that's a difference variety. And then a difference algebraic group is simply a difference variety with a group structure. Or if you want to, you can also say a difference variety is, a difference algebraic group is the group object in the category of difference varieties. And so here the morphisms are just maps given by difference polynomials. Okay. G torsor is a difference variety with an action of G such that for any 2 points in X there exists a unique element in the group that transforms one point to the other point. And so in joint work with Annette Bachmeier, who's also here, we defined an H1 for this setup, so we defined an H1 for algebraic difference equation, and we also showed that it classifies torsors. Okay, so let's look at some examples of difference algebraic groups and torsors. So here the first example is if you take any homogeneous linear difference equation, so here the AIs are can be any elements from the base field, then you know if you have two solutions to a homogeneous linear difference equation, if you add them, you again have a solution. So this shows that the solutions are a subgroup of the additive group. If you look at the associated inhomogeneous equation, so if you just pick any element B from the base field as the right-hand side of the equation, then this no longer is a subgroup. However, if you have a solution to the inhomogeneous equation, and if you add a solution of the homogeneous equation, you still have a solution of the inhomogeneous equation. And moreover, two solutions of the inhomogeneous equation, they only differ by a solution of the homogeneous equation. Okay, so this shows that the solutions of the inhomogeneous equation are a torsor for the solutions of the homogeneous equation. Okay, so that's an example, first example of a difference algebraic group and a torsor. And so, indeed, here one can actually show that every torsor for this group is isomorphic to such a torsor. So, and you can show this using H1. Okay. And in general, it's so for most of the examples, it's easy to come up with some torsors, but then the difficult part is to show that you've actually found all torsors. Okay, and H1 is really good at proving that. Yeah. So for example, but if you try to write down some torsors and you cannot find any torsors, you might guess that there are no non-trivial torsors, and you can try to prove that by proving that H1 is trivial. Okay, so here's another example. That's a difference algebraic subgroup of the multiplicative group. So here, this equation is like a difference monomial, or maybe a Laurent difference monomial. So here the Peters can also be negative, and so this is not the general form of a difference algebraic subgroup of the multiplicative group. So, the general form is that you have finitely many of this type of equations. Okay. And so in this case, if you change the 1 here to an arbitrary non-zero element in the base field, this again gives you a torsor under multiplication here. So another example would be if you look at so you fix an integer d, and you look at all the matrices with periodic entries, with d periodic entries, and you look at the solutions. So that's the group. And if you look at the solution of this equation, sigma to the dx equals ax, where a is some fixed invertible matrix, then this is also a torsor under matrix multiplication. And yes, so for example, if d is 1, this is really just saying that any two fundamental solution matrices, they only differ up to multiplication with a constant matrix. And so that's one of my favorite examples of difference algebraic group. This is essentially the equation of the equation for the unitary group. And so here, again, we can describe all torsors. So using this H1, you can prove that all torsors for this group are isomorphic to a torsor of this form, where A is some invertible matrix. Okay. And already here you can see that it's kind of gonna be hard to show that all torsors are trivial just from knowing that you can solve algebraic equations and that you can solve linear difference equation. Because if you look at this equation, this is an honest non-linear difference equation, which defines this torsor here. All right. Okay, so that's the last example. It's a very small difference algebraic group. So here you look at all g's in GM whose square is 1, and that are fixed by G. That are fixed by sigma. And that's the torsor here. So this is a subgroup of the multiplicative group, and the torsor I'd like to look at is all elements whose square is 1 and that are mapped to minus x by sigma. Okay, so it's immediately, you can check immediately that this is a torsor and a multiplication, but here something surprising happens, and it turns out that this torsor does not have any points in fields. So if you look, if you try to find a point in x over the field, well, the equation x squared is 1. In any field, it only has the solution 1 and minus 1. So since sigma is a ring endomorphism, it will map 1 to 1 and minus 1 to minus 1. So it's not going to be fixed by sigma. Okay, so this torsor is always empty. So this kind of now, if the main question is what condition on the field is gonna guarantee that all torsors are trivial, then at this point you realize, okay, this question doesn't make much sense because there is no such field. Okay, so there is no field such that all torsors over this field are trivial because this torsor is not going to have any point in fields. Okay, so yeah, but if you study this example a bit more, so it does not have a point in field in a field, but it has a point in something which is very close to being a field. And so indeed, if you look at k times k, so k times k is a ring by component-wise addition and multiplication, and you define the sigma on k times k just by applying sigma, but also by exchanging the two elements a and b. So this is how k times k becomes a difference ring, and then you see that 1 and minus 1 is actually a point in the torsor. Okay, so if you square 1 and minus 1, the multiplication is component-wise, so this gives 1. And now if you apply sigma to 1 and minus 1, so applying sigma doesn't do anything, but you shift the two things, so you see that you actually find the negative of 1 minus 1. Okay, and that's kind of a general principle. So in general, you can show that for every torsor, there exists an integer n and a sigma field extension such that the torsor has a point in k to the n. Okay, so here k to the n, it's considered as a ring by component-wise addition and multiplication, so it has a lot of zero divisors. And the sigma does this, so you apply sigma to the coefficients, but you also shift it in a cyclic way. Okay. And even you can actually do one better here. So the n here, you can choose the n here in such a way that it only depends on g. So the k will depend on x, but you can choose the n in such a way that it only depends on g. All right, so that's that. And so now we are ready to look at. Yeah. No, so this in general here holds for all different algebraic groups G. Yeah. Yeah. So in general, you cannot. So we cannot hope for a difference field such that all torsors over the difference field are trivial. However, we can hope for a difference field such that all torsors will have a point in some power of the field in this sense. Okay, so that's how we have to modify the question to make sense of it. And so here that's the main result. So I'm interested in difference fields such that all torsors have a point in k to the n for some n, and where the n actually only depends on the group and not on the torsor. Okay, so there's those three conditions. Again, the first condition is being algebraically closed as before, and then the second condition is very similar to being Picabesiot closed. It has two little twists to it. So first of all, we are looking for solutions in k to the n and not just k as we would do before, and also instead of sigma y equals ay, we also have this power of sigma here. Okay, so but that's really the analog, at least in this setup, that's the analog of being Picabio closed. And now the third condition is really just taking care of the difference algebraic subgroups of the multiplicative group. And so here, so this system of equations here, this is not just the usual exponents. This is these are like Laurent monomials here. So the alphas are polynomials with integer coefficients in sigma. And so here is how this this power of polynomial in sigma is defined. So these are the equations. The AIs are in the base field, and essentially, yeah. So these equations you can think of, yeah, they define what people call a toric difference variety. And so the statement here is, well, if you have a consistent system of such equations, then it already has to have a solution in k to the n. Yeah, and so really this is, so the third condition is really just taking care of the multiplicative groups, or more precisely, of the subgroups of the multiplicative groups. Yeah. And so the idea of the proof is essentially the same as for Pelé's theorem. So you can, so there's a lot of structural results for different algebraic groups, and so using the induction principle, you can use all those structural results to decompose the different algebraic group into simpler pieces, and you work it out for the simpler pieces. Okay, so thanks a lot. Yeah. Mm-hmm. Oh, it's explained down here. So alpha is a polynomial in sigma, and then you do this. Yeah, the addition becomes multiplication in the thing. Mm-hmm. Yeah, so there's essentially two reasons. So, oh yeah, sorry. So the question was, why do we have to have this n here? I mean, I agree. It would be nicer if we didn't have this n, right? So there's essentially two reasons. So one reason was already explained in the example here. Yeah, because we don't, like, if I don't do the n, we cannot have a point. So so for this kind of examples, I need to do the n. But there's also another kind of example, which is, for example, the unitary group is where we have sigma of g is, so one way to write it is like this. So this equation, this difference equation, defines the unitary group, and so here it's, so the equations for this group is kind of so the equations for the torsors for this group are kind of complicated. They are nonlinear. But here, what you can do here, the idea here, the trick is, if you replace sigma by sigma squared, if you do it twice, you obtain that sigma squared of g is actually g. Okay, and this one is so much easier and nicer than this one. And by replacing k with k to the power n, another way to think of it is as replacing sigma with a power of sigma. And so that's actually like a general philosophy in difference algebra, that sometimes things become easier if you replace sigma with higher powers of sigma. And so this one is much easier than this one. And so for this one, you can work it out. And that's what yeah, that's what the n does. Yeah, that's much more interesting than. Yeah, so maybe so it's not fully clear to me, and so but maybe another natural question ask. So I was doing here just looking for solutions in rings, and there is a sort of maybe, let's say, competing approach to different algebraic groups where you only look for solutions in fields, and it's a natural question. You can still just ask, okay, when are all Torsors trivial? If for this other definition of different algebraic groups, and I think I can work it out in that case. So the answer is not going to be as nice as here, but I think it's possible to work it out. But you would so you would need to include. So if you don't want to do that, the thing with the n, right? So then you would need to include the torsors for equations like that, and like so I think it. So using the classification of the automorphisms of simple algebraic groups, I think it's possible to write down a full list of equations that guarantee that all torsors are trivial. But it would be more complicated than that.